Okay, section 3.2, number 7. We're supposed to find the limit of this as x goes to 0. Now, we can look at a calculator, type this into Desmos, and get x closer and closer to 0 and figure this out. But let's go ahead and do C. If x is going to 0, we're going to get f of 6 plus f of 6. And if f of 6 is 0, we're going to get 0 plus 0. And x is going to 0, so the numerator is going to 0. The denominator is going to 0, so L'Hopital's rule applies, which says we can take the limit as x goes to 0 of the derivatives of this. Now, the derivative of f of this would be 3f prime of 6 plus 3x. Would be the derivative of this, of something, so it'd be f prime of this times the derivative of the inside, which is a 3. Plus, the derivative of this would be f prime of 6 plus 5. Is that 0.5? I think that was 5. I think I made the 0.5. 5x times the derivative of the inside, which is a 5, over the derivative of x, which is 1. So, if that's not 0.5, I don't have the book right now to look at it, but as x goes to 0, we don't have the problem we had before. So we get 3 times the derivative of f at, if 0's here, this is at 6, which is 11, and 5 at 6, f prime at 6 plus 5 times 0 is also f prime at 6, which is 11. So we got 33 plus 55 divided by 1. So that's 88 divided by 1, or 88. So that's the slope of this there. Now let's check this one. As it goes to infinity, well, the square root of x squared, that's going to be sort of like an x. It's just going to keep going up and up and up. So this is going to go to infinity. And this is also going to go to infinity because x is going to keep growing. It's going to go towards infinity. So L'Hopital's rule applies. So we get the limit as x approaches infinity of the derivative of this. So this is 8 plus 11x squared to the 1/2. That's not the derivative. The derivative is going to be 1/2 times this to negative 1/2. So it's going to be 8 plus 11x squared times 1/2. And this would be to the negative 1/2 times the derivative of the inside, which is going to be 22x, divided by the derivative of this is just going to be 8. So now what happens to this as x gets large? Well, we need to realize that this is the square root, but in the denominator. So we have the limit as x is getting large of 1 over 2. This should go in the denominator. There's an 8 down there already. And this is the square root of 8 plus 11x squared and 22x. Now, as x gets really large, this gets really large. And as x gets really large, this also gets really large. So we do not know yet, but we can try the derivative again. So let's see, the 2 can go into 22 and make 11. And so we get the derivative of the numerator. Derivative of the numerator is 11x. No, 11. And the derivative of the denominator is 8. And this is to the 1/2, so it'd be 1/2 8 plus 11x squared to the negative 1/2 times 11x. No, times 22x. Well, let's see. That's a little hard to read there. Let me rewrite that. The limit as x approaches infinity. We have 11 and we have a 22, so that reduces to a 2 in the denominator, which would cancel the half, and we'd get 8. And the 11 is gone. This is to a negative 1/2, which would bring it to the numerator again. 8 plus 11x squared. And we took care, they've got the 8. We've got the 11 going in there, 22, which cancels the 2. So that's what we're trying to find out what's going on. And this, as x goes to infinity, this will go to infinity. And this doesn't go to infinity, so we can't do the rule again. And so it goes to infinity. So enter I for infinity, which is what we'd have to do. And number 14. A function g dominates f provided that as x goes to infinity, and they both go to infinity as x goes to infinity, and f over g goes to 0. It means g grows faster than the numerator so that the fraction goes towards 0. Which function dominates, ln x or the square root of x?
Are those bottom eggs?
Yeah, bottom. So, I'm going to guess ln, which goes like this, and the square root goes something like this. Not sure which one's higher, so let's take a look at it. So go to y equals and we'll look at ln of x and square root of x. Oop. Zoom 6. There's ln. There's the square root. And it looks like the square root stays above the ln. I need to look over further, so I'm going to go to 50 in the x's. There's the ln. And there's the square root, and it looks like the square root grows faster. So I want to put the square root in the denominator. So I'm going to find out if by doing the limit as x approaches infinity of ln x over the square root of x. And this is going to go to infinity. Both of them keep going up and up and up till infinity. So I can take the derivative of the numerator, take the limit as x goes to infinity, after I take the derivative of the numerator, which is 1 over x, or derivative square root of x, that's x to the 1/2. Its derivative is 1/2 x to the minus 1/2. So that would put the x to the 1/2 in the numerator, and this x would go to the denominator. This 2 would go to the numerator. So this is the 2 comes up, the x goes down, and the square root of x comes up. And square root of x is the 1/2 power. We can reduce this by subtracting the powers. So this is the limit as x goes to infinity of 2 over 1/2 from the power 1 is 1/2. And this does not, that both don't go to infinity now. So we can't do L'Hopital's rule. But this is a constant that's being divided by something that keeps growing larger and larger and larger, slowly albeit, but larger. So this is going to go to 0. So it is correct that this dominates this. The square root dominates ln x. And does any nth root dominate ln x? Well, let's go to a different one. Let's go down here instead of x to the 1/2. Let's go x to the 100th. That might be pretty small. I'm going to go up and turn this plot off and push graph. There's the ln, and here's the other one. It's starting to creep up, but we can't really tell until we go further out, probably a long way out. There's the ln. And that one doesn't look like it's going to dominate. But we can check it. So we're doing now the limit as x goes to infinity of ln x over x to the 1 over n. And these both keep growing, so we're going to have to do L'Hopital's rule. So we get the limit as x goes to infinity of 1 over x, that's the derivative of ln x, and in the denominator we get x to 1 less than 1/nth, so it's going to be negative, so it's going to be x, so I'm going to put in the numerator x to the 1/nth, so n minus 1/nths over at times 1/nth. Now, if I take this is x to the 1 minus 1/nth. Let's see, is that correct? We've got to reduce this by 1/nth divided minus n nths is 1 minus n nths. This minus 1 is this, which, if I bring it to the numerator, it changes its sign and turns this around to be n minus 1 over n. Or I could write it this way. This might make more sense to you. Let me write it this way. The limit as x goes to infinity of the derivative ln x is 1 over x, and the derivative of this is x to the 1 over n minus 1 times 1 over n. Take and reduce the power by 1. Well, if I multiply x times this, I add the powers, so this is to the 1 and this is minus 1. This 1 over n becomes n in the numerator, and this becomes x to the 1 over n in the denominator, because the 1 and the minus 1 cancel, and this will grow, this does not, and so this goes to 0. So this will dominate this as long as n is any positive integer. They want it to be a positive integer. Yeah. Okay? Explain why e to the x will dominate any polynomial. Okay. Ooh, I hope that wasn't off the screen. That may have been. Explain why e to the x will dominate any polynomial. Well, we'd be doing the limit as x approaches infinity of e to the x in the denominator, if we think it dominates, and the numerator would be x to like 5 plus x to the 4 plus x to the 3, or with some numbers in front of them. But it doesn't matter. As we take the derivative of this, we get e to the x. And as we take the derivative here, these powers keep decreasing until we'll eventually end up with a constant. We'd have the limit as x approaches infinity of a constant over e to the x, and this will grow to infinity. That will stay the same, and so this will go to 0, so e to the x dominates anything. And x to the n will dominate ln similarly, given any two nonlinear functions such that neither dominates the other. Two nonlinear functions that don't dominate each other. How about if you do e to the x and 2 to the x? When we get, as x goes to infinity, you're going to get, this is going to go to infinity, that's going to go infinity. So we can do L'Hopital's rule, and this will be ln 2 times 2 to the x, and this would still be e to the x, and this will just keep happening. We'll get more ln 2s and ln 2s, and neither will dominate each other.